So last time, oh, tell me I didn't bring my notes. Ah, rats. Well, here goes. So last time I introduced the concept of the Lorette decomposition, right? And we worked some examples of how that shakes out, right? But basically it says that if f of z is, let's say, holomorphic on an annulus, then we can write f of z equal to the sum k equals minus infinity to infinity of a sub k times z minus z naught to the k. And let's say this is an annulus centered at z naught. Now that's not how I presented the Laurent decomposition to start with, right? I tell you there's an f0, there's an f1, such that f1 is, f0 is analytic to the center of the annulus, right? And f1 is analytic outside the inner radius of the annulus, right? But then at the end of class, I said, well, what does that mean? That means that there's a power series that gives you f0, there's another power series that gives you f1, but the power series that gives you f1 is in terms of reciprocal powers of z minus z naught, whereas the power series that gives you f0 is in terms of just, you know.
I have your notes pulled up.
Oh, yeah? Thank you. That's cool.
You just use double finger to scroll.
The double, ooh.
That's not touching.
Oh, not a touch screen. That's good, because I was assuming it's a touch screen because so many things are, you know, but I'm glad it's not. All right, so this is what's called a Laurent series, right? And what we want to do today is to understand what's the significance of the coefficients in the Laurent series, and we want to characterize different cases, all right? So like the first order of business is to think about, see, where am I? And of course, I think the other thing to you know, just to comment on from last time is that the geometric series is so much of like the examples, like must understand geometric series. If you really have mastered the geometric series, you can do most of my examples, right? Anyway, so here what we want to do is we're going to integrate the given function above, f of z about, I should say around, z minus z naught equals to r, all right? Counterclockwise oriented, all right? So integral over this circle of radius r, all right? F of z dz. All right, so that's going to be the integral around, I'm going to call this thing CR to stop writing that, all right? Integral around CR of the sum, k equals minus infinity to infinity of a sub k z minus z naught to the power k dz, right? But in fact, if I'm more fussy, and if you sort through the theorems that we did, you'll find out that this Laurent series is not just any old series on the annulus, it's actually uniformly convergent. In fact, normally convergent on the annulus. Any converges on any closed subannulus is the meaning. And as such, I can commute the order of the integration and the summation. All right. All right, so And then I would remind you of a calculation we did earlier, which was integration of z minus z naught to a power around a circle, right? We learned that that is 0, except in one case, except in the case that k equals minus 1. So this integral, and I've lost my coefficient. There's still an a sub k out here, right? But this integral,
Can't you only have integer powers if
if
is that not the case?
can I only have what powers?
Integer powers.
Integer powers. Well, yeah, these are integer powers. That's what we're dealing with here. That's the Laurent series. In contrast, in differential equations, if you've taken differential equations and you've studied what are called Frobenius series, there you have non-integral powers. So people do look at series with non-integral powers, just not here. So this works out to 2 pi I Kronecker delta of k comma minus 1. In other words, it's 0 for every single possible case except for k equals minus 1. So this infinite sum of terms collapses to just 2 pi I times a minus 1. This is very, very neat. What this means is we can integrate a function, right? We can integrate a function about a circle centered at z naught by merely calculating its Laurent series and picking off the minus 1 coefficient. That's very nice. All right. Now, so let's look at an example of that right quick. So if you were going to say integrate around the unit circle, let's say like sine of z dz over z to the 4th. All right. So that would be a pain in our previous way of thinking because we would have had to use not too much of a trouble. We'd have to use Cauchy's generalized integral theorem with m equal to 3. That would have forced us to do 3 differentiations and, it's kind of a drag. But here, what we're going to have is, what's the Laurent series for sine of z over z to the 4th is my question, right? So we have 1 over z to the 4th, right, times z minus 1/6 z cubed plus 1 over 120 z to the 5th plus dot 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 dot. So we just have to multiply through the 1 over z to the 4th to find the Laurent series here. It's just 1 over z cubed minus 1 over 6z plus 1 over 120z plus dot 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 dot. All right. So the singular part of this Laurent series with respect to the expansion about 0. In other words, the singular part's the part that has negative reciprocal power, like negative powers, the reciprocal parts. Right? Those are the parts that are divergent. If those are absent, then it's just analytic, and so we know that it's holomorphic, and we know that the integral around the circle would just be 0, right? But anyway, here, what is a sub? So this has a sub minus 1 equal to minus 1/6. See, that's the coefficient of the 1 over z term. And so what the answer is 2 pi I times minus 1/6. Or if you like, minus pi I over 3. That's, it's a really nice result, isn't it? I did a more complicated example in the notes, but let's see here. See, there's something else I wanted to say. I'm trying to. What if instead of integrating f of z, you wanted to integrate, you could also do this, right? The integral of, say, f of z dz over z minus z naught. This time I'll do n plus 1. Right? How would that sort out if we again do it over the the circle of radius r?
Do you not use Cauchy's here to simplify it a little bit?
We could. I want to connect. So what I want to do right now is I want to connect the calculation we're doing here, right, which is just a series calculation, with the generalized integral formula of Cauchy. Exactly that. You got it. So I'm now suspicious of my mics this week after the trouble. This one's actually stereo. It's very exciting. People will get to hear me in the right ear for this lecture. Don't get used to it, though. This mic, it uses AAA batteries, and I've had trouble with it before. I can't remember what the trouble was. I think I had like interference with some nurse or something, where I used to teach. I had nursing, and one lecture I completely lost, and it was just full of like anatomy stuff. It was really unsettling. So the same calculation we just did, right? I'm just going to skip a little bit ahead. You get sum k equals minus infinity to infinity what? A sub k integral over the circle, but this time what? Z minus z naught to the k what? And then we're dividing by this, right? So minus n minus 1 dz, right? So exact the same calculation I did over here, just now with the dividing by that reciprocal of z minus z naught. And once more, I would remind you we calculated this particular complex integral early on in our story of complex integration. And again, by the same result, this is 2 pi I. This time, Kronecker delta of k minus n minus 1, comma minus 1. All right. In other words, the only time that integral is non-zero is for the case k equals to n. K equals n is the only non-trivial contribution to this integral. And so what we have is equal to, 2 pi I a sub n. Right? Now, what else did we know about this? What else can we say? Cauchy's generalized integral formula told us this was what?
Oh, that an is just fn?
F.
But it's 1 over 2 pi I though. Cauchy is like 1 over 2 pi I f to n.
Okay, great. So we could say an is equal to 1 over 2 pi I, right? Integral of f of z dz over z minus z naught to the n plus 1, right? And your point was Cauchy's generalized integral formula said that was what? That was the nth derivative. The nth derivative evaluated z naught divided by n factorial, I believe.
Yeah, so we're saying, okay. Oh, so we have a sequence for Cauchy's integral formula?
Well, see, I should be careful here, right? We can only, so this, Cauchy's generalized integral formula, right? What are the terms and conditions to that? Do you remember?
Circle.
It's a circle, okay. Well, I guess it doesn't have to be, but Cauchy's generalized integral formula assumed f of z holomorphic inside and near the circle CR, right? So f of z was playing nice, right? All of the bad acting of the integrand is coming from the division by the z minus z naught, right? And the interesting thing is, whatever that, diverging behavior of dividing by z minus z naught is, it's washed out in the details here, and it just boils down to, well, it ends up just being the nth derivative of z naught divided by n factorial, right? So this, on the other hand, does not make sense. May not be possible for f of z, which is merely holomorphic on annulus centered at z naught. So like I cannot write that equality unless I'm dealing with a function, right, which is in fact holomorphic at the center of the annulus we're talking about. So this is really a very special case. The integral, on the other hand, I can do. Again, provided that that circle, the circle has to be where? So remember that there's the, what do we call it? I can't remember which one we used for sigma, which one we used for rho. Do you remember?
I think rho was the first, sigma was the next one.
Okay. Hope you're right. All right, good. So the circle here has to be somewhere, excuse me, somewhere in here, This is CR, right? Okay. So, I tie this all together in theorem 6.18, the Laurent Series decomposition, which basically just restates what I wrote, okay? So now we're going to talk about isolated singularities. So I guess I can erase, I'm going to erase this actually. What is an isolated singularity? So remember we talked about isolated points, right? Yes. So that's the sense in which I'm using the word isolated. There are three kinds. All right, there are three kinds of isolated singularity. First of all, let me just give you a definition. A function f has an isolated singularity at z naught, right? If there exists r greater than 0, such that f is analytic zero less than modulus of z minus z naught less than r. In other words, it's an isolated singularity at z naught if you can look at a little disk centered about z naught, and the only point where the function fails to be holomorphic is at that point z naught. All right? Now, definition. We say, well, here, suppose f of z has isolated singularity, z naught, then number one, if f of z is equal to the sum k equals 0 to infinity of a sub k, z minus z naught to the k, all right? So, just to preface this definition, if it has an isolated singularity, that means that it is holomorphic on the punctured disk centered at z naught, right? Which is, of course, a special case of an annulus, which means that we have a Laurent decomposition, which means we have a Laurent series decomposition of the function, right? And so this definition I'm giving you is breaking down the nature of the singularity in terms of how the Laurent series works out, okay? So this one, the reciprocal terms are absent. Notice it starts at k equals to 0. Okay, so basically, f of z has a power series expansion on the deleted disk, all right? Then this is called a removable singularity, all right? Z naught is a removable singularity. All right. 2, if f of z is equal to the sum k equals minus n to infinity of a sub k, z minus z naught to the k, then z naught is a pole of order n. A pole of order n. So some special lingo here. N equal to 1 is simple pole. N equals to 2 is double pole. All right. Simple pole, double pole. All right. And if f of z is equal to the sum k equals minus infinity to infinity a sub k, z minus z naught to the k, where infinitely many a sub k with k less than 0, not equal to 0, then z naught is essential singularity. All right. So I can give you an example of each case. Yeah. Probably a good idea. So an example of case 1. Usually the example is given something like this. F of z is just, like e to the z minus 1 over, oh, that's not it. My bad. Try that again. E to the, it's about sine, sine of z over z would be an example of that. So here, you've got 1 over z times z minus, 1/6 z cubed plus dot 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 dot, right? So what you get 1 minus 1/6 z squared. The next one's over 120, 5 factorial. So I'm referencing the known power series expansions of sine here, right? So, to be fussy, f of z is not defined at 0, right? But it's easy to extend f to a continuous function on the disk, Well, this calculation is good for the punctured plane, If I just, instead of using this as my definition for the function, if I define a new function by the power series over here, it's an entire function. It's actually, holomorphic on the whole complex plane.
Does it not turn to cosine?
That's not cosine, no. Cosine starts with 1, but then it has minus 1/2 z squared.
Okay.
Yeah. But, yeah. An example of 2. Lots of things are possible, of course. Here's one. E to the z over z to the 42nd power. All right, so that's like 1 plus z plus 1/2 z squared plus dot 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 dot, Eventually you get 1 over 42 factorial, z to the 42, and so forth, yeah? Divide that all by z to the 42, what you got? You got 1 over z to the 42 plus 1 over z to the 41 plus 1 over 2 z to the 40th plus dot dot dot. Eventually, you get 1 over 41 factorial, z, and then plus 1 over 42 factorial plus 1 over 43 factorial, z. Anyway, it's kind of a ridiculous example, but I did it mostly just so I could point out to you that this piece right here, I would refer to as the singular. This is the singular part of the Laurent expansion at z not equal to 0, right? And so that's a pole of order 42. Example 3 would be something like, typical example is something like e to the 1 over z. If you look at e to the 1 over z, what's its power series? What's its Laurent expansion? Well, it is just 1 plus 1 over z plus, 1 over 2z squared plus dot 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 dot. See, the singular part of this one is all of this, right? Singular part. And as you can see, the singular part here has reciprocal powers of arbitrarily high degree. So this makes 0 an essential singularity of this one. So this is easy enough to understand, right? These are the 3 cases for the Laurent series. Either the Laurent series is really just, it's almost just a, there's really 4 cases, right? So if you think about a Laurent series centered at z naught, right? Either the z naught is an isolated singularity or it's not, right? If it's not an isolated singularity, then f of z is holomorphic there, and you just have a regular plain old power series, But if it is isolated singularity, and the Laurent series is just a power series, well then it's removable singularity. If you've only got a few offending reciprocal terms, it's a pole of order n. And if it has infinitely many singular terms, then it's an essential singularity. And the behavior of functions with these different types of singularities is very, very different. Right? And that's the next triple of theorems concern. How do we characterize such functions? So theorem 1 is on Riemann's theorem for removable singularities. It says that if you have an isolated singularity, z0 of f of z, if f of z is bounded near z0, then f of z is a removable singularity. So theorem for f of z with isolated singularity z0. If f of z is bounded near z0, then z0 is removable singularity. In other words, or another way to think about a removable singularity is it's the complex analog of like a hole in the graph. It's pretty much that. All right, so let's talk about the proof of this one. So the proof is essentially just by the Laurent series, right? So you have the modulus of the nth coefficient of the Laurent series, right? What's that equal to? What did we just write? Remember we wrote 1 over 2 pi I integral of a circle sufficiently close to z0, right? So this, to be more clear, it's the z minus z0 equal to, let's say, r, where r is where f of z is holomorphic, yeah? Okay, and then we have f of z dz over z minus z0 to the power n plus 1 in the denominator. We're taking the modulus of this whole thing, right?
Will we apply Cauchy's first?
Apply what?
Will we apply Cauchy's theorem first?
Oh, no need for anything so hard as that. We can just use the Ml theorem because, so this is, we already know this from what we talked about earlier today, right? This is the generalized, this is the combination of the generalized integral formula and the Laurent decomposition. It's those two things put together, really. But we're assuming that what? F of z is bounded, if f of z is bounded. So this is less than or equal to what? That bound, m, divided by 2 pi, right? And then what is this? On the circle, that is just r to the n plus 1, right? And what's the Ml theorem, right? So what I'm trying to, so I'm not being very clear here. Let me say it this way. M over 2 pi r to the n plus 1. This is a bound on the integrand. If I move the 1 over 2 pi I inside the integration, this is a bound on that integral, right? And then what's the length of the integral? Well, it's the curve 2 pi r, right? So what do we have here? We have m over 2 pi r to the n, right?
You have m over rm.
Oh, yeah, okay, duh. Sorry, r to the n, yes. Now what happens with that?
That goes to infinity. If you apply the sequence, that means the bound would go to 0. I'm sorry.
Yeah, let's see here. For
The bound on the it approaches 0.
let's see, I say as r goes to 0, we find that the modulus of a sub n goes to 0 for n less than 0. So the picture of what's going on here, right? We have the isolated singularity z naught, right? And we've got this circle centered, radius r, and we're letting r go to 0 to shrink down on that point. As we do that, this will diverge, won't it, if n is positive?
Wait, like, is n staying constant, or r? No, r's changed, right? N staying constant?
Yeah, we're fixing n and thinking about what happens here.
Yeah, if you fix n and r,
fix n, let r go to 0. It diverges. Unless n is what?
0.
No, think about this. If n is negative, right? Like if n is minus 2, for example.
Oh, it gets bigger?
This m over r to the n is actually mr squared, right?
So it gets bigger.
So if n is negative, this goes to 0 as r goes to 0.
Yeah, r goes to 0.
All right. Now, if of course, if n is equal to 0, well, this just gives you m, doesn't it? If n is positive, then this, I think this diverges as r goes to 0. That's true. But anyway, that doesn't concern us. The point is that I think the formula stops, well, anyway, let me stop talking about what the proof is not talking about. So because the point here is if n is less than 0, then we get that the modulus of a sub n goes to 0 as r goes to 0. Which leaves us with the case that the Laurent series is just of this form, right? It's very dumb. It's very dumb what I'm getting confused about, Audric. I'm like, well, if n is positive and r is going to 0, this is infinity. So that must mean that this is infinity. No, it's not useful. It's just, this is bigger than that. Infinity is bigger than a sub n, yeah. True, but not particularly instructive. But in the case that n is negative, r goes to 0 forces this to 0, which gives us the removable singularity. So if the function is bounded near the isolated singularity, it's a complex hole in the graph. It's a removable singularity, right? Don't ask me to draw the graph. Right? Oh, my example is sine of z over z. Duh. Okay, so next. I define, I give more language on the next page. I called it the singular part here, but oftentimes this is called the principal part. Principal part. Principal part of f of z about z naught. All right, great. Theorem. Let f of z be an isolated singularity of f. Then z naught is a pole of f of order n, if and only if. Oh. All right, so here we go. I guess I can erase all this now, yeah. Oh, I shouldn't have erased that. I could have used those words. My bad. I'm foolishly looking up at that clock as if it has something to tell me. So theorem, if f of z has isolated singularity at z naught, then f of z has pole of order n, if and only if f of z is equal to g of z over z minus z naught, to the n, where g of z is analytic at z naught. So this is one theorem we have to characterize a pole of order n. All right? And so like the proof of this, right? If you think about this, the proof is actually pretty nice. So f of z is a pole of order n, right? What's that mean? That means f of z is equal to like a to the minus n over z minus z naught to the n, right? Plus dot 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 plus like a minus 1 over z minus z naught, yeah? Plus, you know, a0 plus a1 z minus z naught, etc. So what do? You just do what? You just pull out, factor out 1 over z minus z naught to the n, right? And what are you left with? You're left with a minus n plus, you know, the next one would be a minus n plus 1, z minus z naught, yeah? Eventually you get to stuff like a naught times z minus z naught to the n, and so forth. Anyway, the point is, we have the convergence of the series, the Laurent series, on the punctured disk centered at z naught already from the assumption that this is the Laurent expansion. And as such, this series that I've just written in parentheses is a convergent series centered about z naught. In fact, it's a power series, right? Therefore, the function which is defined by this series, let's call it g of z, analytic at z naught, because it has a power series expansion. So there's the forward implication, right? And the reverse implication of this proof is very, very similar. See, because if you have g of z is analytic, right? So g of z is like, you know, some k equals 0 to infinity of like, you know, b sub k z minus z naught to the power k, right? If you do that, and you have f of z is what equal to? It's equal to g of z over z minus z naught to the power n, yeah? By assumption, in the converse direction of the proof. So all you do is plug that series in there, what you got. And to make it manifestly what we want, I mean, it's just a matter of, do you understand what you're looking at or not, you know? If we let j equal to k minus n, then j is equal to minus n when k is equal to 0. And so this series can be rewritten as the sum j equals minus n to infinity of b sub j plus n z minus z naught to the power j, which is manifestly a Laurent series that has a principal part which starts at order minus n. In other words, it's a pole of order n, which is what we were trying to prove. There's another very, very related theorem to this about poles of order n. This one is often very useful. Theorem F has pole of order n at z naught if and only if 1 over f has 0 of order n at z naught. Well, it's a little bit more than that. 1 over f is analytic at z naught with a 0 of order n. How late did I start today, Audric?
I don't know, it's 4:06 though.
Yeah.
I am dumbfounded by this school.
You're dumbfounded?
Yes, by financial aid specifically.
Oh. Well, you tell me more in about 3 minutes and 11 seconds. Wait a minute, 4 minutes and 11 seconds. Now, I could go through the proof of this, but I think I'd rather spend the remaining minutes talking about the big word we want to use to describe what we're talking about, all right? So I'll try to do examples of this and such. I mean, in the next, I'm going to make a video because we're not going to meet Friday, so in the video I'll give you some examples, but I do want to include this definition in this talk here. Definition. A function is meromorphic on a domain D if it's analytic on D except possibly at isolated singularities, each of which is a pole. Definition. F of Z is meromorphic on domain D if f of z is holomorphic on D except at isolated singularities, each of which is a pole. There you go. Yes, or so I took this class in something called vertex operator algebras when I was in graduate school for physics. I got yelled at by the graduate director of physics. What are you taking this course for? Who do you think you are? I'm like, I'm a person who's interested in vertex operator algebras, is who I am. And not to mention, I heard that this guy only gives A's and doesn't assign homework, so it sounded like a good deal in an otherwise busy semester. And it was just enjoyable. But the professor's name was Takashan, if I remember right. And he was actually a physicist. Oh, because he thought I should be taking something that was more low level and helping me pass my qualifiers or whatever. I'm sure he had my best interest in mind, but anyway, I love that course partly because the instructor said meromorphic many times in this course. He used to always talk about meromorphic functions, and the way he said meromorphic, it gave me joy. The other thing that gave me joy in that course was his ability to write pi, like beautiful. His pies were just beautiful. They had like just perfectly curled bits and pieces. Like his pies were just immaculate. But anyway, meromorphic function means it's really the thing complex analysis is more interested in ultimately is meromorphic functions as opposed to just holomorphic functions, because meromorphic functions are the functions for which we can do the kind of calculus I've showed you today a little bit of. So the meromorphic functions have pretty understandable behavior. So because isolated singularities that are either removable or a pole of order n, we can do some pretty careful calculations for that are quite manageable. The theorem for essential singularities, right, which I don't have time to write on the board today. Well, I can tell you one other thing. A pole of order n, one more natural result that we know for it is if you have a pole f of order n greater than 1, if and only if the modulus of f of z goes to infinity. as z goes to z naught. So if you approach z naught, if it's a pole of order n, it goes to infinity. The modulus goes to infinity. That makes sense, right? Essential singularities have weirder behavior. So here's the Casarati-Weierstrass theorem. It says let z naught be an essential singularity, isolated singularity of f of z. Then, get this, for every complex number w naught, there is a sequence zn goes to z naught such that f of zn goes to w naught as n goes to infinity. So essential singularities, they're not bounded. I didn't say that. But they do have this weird property that you can find a sequence that goes to them, and f of zn will go to w naught. But it's a little bit weirder than that still. For every complex number w naught, there is a sequence such that f of zn goes to w naught as n goes to infinity. But there's a little bit more than that. There's something else that's Picard's theorem, which states that essential singularity z naught for all w naught except possibly one value, there is a sequence for which f of zn is equal to w naught for each n. So let's see, it's a little bit hard to, it's like not only, so this is saying that you can find a sequence like, so the sequence is, right? And that sequence goes to z naught, such that the values of the sequence tend to w naught, right? Picard's theorem says that for an essential singularity at z naught, for all w naught except possibly one, you can find a sequence that, so this sequence, I'm not saying that the values of the sequence are f of w naught as they go, but Picard's theorem says you can even pick a sequence such that f of zn is equal to w naught for each n as you go. In other words, it's behaving so badly that you can sample that complex number as you get arbitrarily close. In other words, like an essential singularity is taking all possible values of the complex number plane as it's getting close to that essential singularity. It's got everything close to that point. It's so jumbled up. So for example, the example in my notes, e to the 1 over z, that essential singularity, the exceptional value is 0. Like you can't get something that's identically 0, but anything else like I, you could find a sequence that f of that sequence is I for 1 over z anyway. So essential singularities have some pretty weird behavior, but they're also kind of understandable if you think about just my mental picture of it is it's taking on all values of the complex numbers system as it's getting close to that essential singular point. But anyway, so more in the video. I'll stop here. And you can tell me about the harder things to understand at this university.